And it's our last YouTube all year ever. Yay!
Oh, what a shame.
Oh yeah, you're so it's so heartfelt.
You can hear me in the screencast.
Yeah, I'm sure we will. So you're right here with the mic.
Yeah.
Okay. All right, all right. Shh. Oh yeah, you're here. Did I mark you here? Alrighty. All right, so let's take a look at number 4 on our last worksheet, which is down here somewhere.
Mr. Garcia.
Here it is.
Yes,
No.
Charlotte.
I had
Show
to
more.
rummage through my things, but I found
Oh,
4A.
there's a thing.
Word A, what am I here?
By the way, you can still make up 108, 107. Haven't done those. But this one you can't make up after it's over. It's there. All right, so number 4 says the equation. Yeah. The equation for the charge Q of T on a capacitor in a circuit with inductance L, capacitance C, and resistance R satisfies the differential equation L Q double prime plus R Q prime plus Q over C is 0, where Q is a charge in, what are we measuring charge in? Oh yeah, coulombs. And R is in ohms, L is in henries, capacitance, C is in farads, and dQ dt is the rate of change of the charge over time is amperage, right? That's the current in amps, right? Okay, there you go. So given that L is 1, and R is 2, and C is 4, can you solve for Q? Now they want just a general solution, not giving you initial conditions to figure out the A's and B's.
So it's just like
So you're not, yeah, that's it. And it's an LRC circuit. So notice what we're doing is we're taking the resistor as if it were, as if instead of Q, what if it was S, displacement? So it's S double prime, S prime, and S, right? Yeah. S being the displacement or the, right? The, what do you call it? The Hooke's law, right? The resistive force against the compression, right? And this is directly proportional to like the velocity, right? So that's your resistive, that's your, what do you call it? Your friction type, it's like your friction. So that's why we call that a resistor. All right, so let's solve this thing. Here we go. So 4A, we've got 1 Q double prime plus 2 Q prime plus 1/4 of Q. Right? So now remember we did this the hard way last time. We said, okay, let Q equal e to the RT, plug it in, blah, blah, blah. But can you skip all of that? What's a characteristic equation?
Isn't that what the sign is?
R squared plus 2R plus 1/4. No, just 1/4, right. Right, because if we plug in Q is e to the RT, they all have e to the RT. We factored that out. And then we just left with 1/4 here. And who just came in? Jared. And do we have any homework? No, okay. Alrighty. Alrighty, so solve that. Now, how do you solve that? Can you factor that? Yeah, what?
Quadratic equation. Yeah.
Quadratic formula? This is a quadratic equation already. You want to apply the quadratic formula to it? Okay. Alright, so R is what? Negative B, plus or minus square root of B squared, which is 4, minus 4 times A, which is 1, times C, which is 1/4, all over 2 times A, which is 1. Okay. And 4 times a fourth is 1, so 4 minus 1 is 3. So you got negative 2 plus or minus rad 3 over 2, which is 2 irrational roots, 2 real roots, yeah. This is 1, right? Do you guys do something called Senior Sunrise?
Yeah.
When was that?
Beginning of the
It
year.
was a long time ago? No, my kid did it today. All right, just curious. Every school does it different. Okay, so there you go. So what's the solution? I just want the general solution. All right, so Q of T is going to be what? What you get on the homework? A e to the one of these. How about negative 2 plus rad 3 over 2 T plus B e to the negative 2 minus rad 3 over 2t. Okay? Now notice that the discriminant was what? What was such about the discriminant? Positive, right? When b squared minus 4ac is positive, right? When this, what's in the radical is positive, we call this overdamped. In other words, if you graph the solution, if you got the a's and the b's and you graph the solution, it wouldn't oscillate at all. So the current wouldn't be like an AC current. It isn't positive and negative and positive and negative, even if it's decaying, right? It's just, it's always positive and it decays. Or it's always negative and it decays, right? All right, this is 109. All righty. So we call that overdamped. Now, how would you check this? Let's say you didn't know, you're not sure about this, maybe you messed it up.
Do it backwards.
You want to wait to 109? Oh. Hello, how you doing?
Did you ever play Pluto? Did you ever play Pluto? No. I'm not that good. My brother's playing.
And Aurora. Okay. Alrighty, so now, how would you, can you check this? Is there a way to check this? Isn't there DE solve in the calculator? Have you ever done that with a second order differential equation? By the way, why is it called second order? Because it's got a double prime, right? That's all. Second order ordinary differential equation. What's an ordinary differential equation? Equations that don't involve calc 3. You ever hear of partial derivative? Partial differential equation? Oh, you're going to have so much fun next year. In 3 dimensions with partial differential equations and triple integrals. And, yeah, double integrals and funness. And the div and the grad and the curl and the del and the... What are you talking about? Stokes theorem, Green's theorem, all that stuff. Oh, fun. Oh, so much fun. All right. Anyway, so there's your overdamped case. All right. So now, go back to the question. So that's when L is 1, right? Now, what's the next part? Right now it's 1, 2, 4, but now it says, okay, do the same thing but make it 1, 1, 4. So reduce the resistance. What happens? Okay. Well, wait, were we going to check it? Let's wait. I meant to check this. I want to check this. So I'm going to check this on the calculator, okay? Now, where's my calculator? So just enter the... You do have a calculator. It's right in front of you. It's called CarmT. Yes, it is. I'm going to use it right now. All right, where are you, CarmT? Where are you? Where are you? There he is.
Yeah, it's not here.
It's not here. Go away. What you doing? Would you hide it?
No, because I loaded it and it took a while.
Oh, it's taking a while. Yeah. Well, how do you like my new background? That's the background I use at home. It's just it's 30 graphs from 30 pictures from the Hubble telescope. All right, so let's make a document. Let's make it a calculator document. Let's go into menu. Let's go into calculus. And it's near the bottom, is it not? Differential equation solver. Hello? Okay. So, what do you enter? What was it? Q double prime plus 2Q prime plus Q over 4? As a function of t, you want to solve Q as a function of t? All right, so let's see. Q. I'm going to do double prime. You go over to prime. Hello. But you do it twice. Okay, there's Q double prime. All right, plus 2 Q's. Q, 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 there it is. Right, it doesn't have to be Y's and X's all the time. It's Q's and T's today. Plus Q over 4. It's Q prime. It's Q prime. You're right. Ooh, that would mess the whole thing up. Yeah, Q prime. So I need a prime. There you go. Plus just Q over 4. Not Q prime, in other words. And where's 4? There it is. All right, comma. What goes here?
1/4.
No. We got the 1/4 already.
Q.
No. T, the independent variable, goes first, comma, the dependent variable goes second. And let's see if this calculator can handle this kind of a solution.
I can't handle it.
Argument error. Why? Why? Wait, I just did this the other day. It worked fine.
Yes, we can't do counting.
Wait, no.
Oh, yeah, you didn't use to.
I didn't use what?
T is a thing.
T in what thing?
The thing that you do there.
What are you talking about? Can you be more vague? Try and be more vague, okay?
Okay.
Wait.
I can be more vague.
Wait, I just think, wait. It doesn't like Q and T, maybe? Is that what it is?
Yeah, I think so. Let's use.
Oh, wait, I didn't write the whole equation.
It's not there.
Oh, you need the whole equation. What am I doing? Oh, it's too early in the morning for this. It's an equals 0, don't forget. Duh. Got to equal something.
Next to the thing.
And the thing, right, that thing. Ah, da-da. All right, is that what we said? That's what we said, right? Da-da-da. All right, so we checked our work. We just want the general solution. They called it C2 and C1 instead of A and B, but big deal, okay? And then we had, let's see, what was it? -2 plus rad 3 over 2 that just reduced the -2 over 2, right? And -2 minus rad 3 over 2, so again, they reduced the -2 over 2, big deal. -2 over 2 is the -1. It's the same thing. Yes, perfect. Okay. So let's do it again. So 4b. All right, so now we're perturbing the problem a little bit. We're reducing the resistance to 1 ohm instead of 2 ohms. All righty, so we have 1 Henry, 1 ohm, and 1/4, no, 4 farads. It's over C, right? So C is 4 farads, okay. So we didn't change anything but the resistor, right? This is called an LRC circuit. All right, so how do you solve this? The characteristic equation is now R squared plus R plus 1/4. Okay, so R equals -1 plus or minus square root of 1 minus 4 times 1 times 1/4 all over 2 times 1, right? So again, a 4 times 1/4 is a 1, and 1 minus 1 is 0, so you get 1 root. This is a problem. We need the behavior with 2 roots. We need 2 branches. So do you see what's the problem? It's not, it's not 2 different roots like before? Yeah, so can I do what we did before? That Q of T is A e to the 1 root plus B e to the other roots? Wait a minute, what? That's just C e to the -2t.
Oh, B times T.
Yeah, why is that? Why do they, what's the justification? I can never get the justification for why you need the T. I know you need it, but why does it work? That's my question. That's a mystery from Calc 5, linear algebra. Yeah, that I forget. I actually forget that. This is wrong. This is what's called, notice what the discriminant was. What's in the radical? 0. When b squared minus 4ac is 0, we call this critically damped. And what it looks like is like the Cadillac car thing that we talked about. You have an insult to the shock absorber, but it recuperates real fast. So it dips and then it settles down. So it oscillates in that it's positive, then negative, then settles down, right? That's what it looks like. If you had the A and the B and the initial conditions to get A and B and so forth. But that's not what this looks like. This is just exponential decay. It just goes like this, right? That's not the answer. What they tell you in linear algebra is that you have to have a linear combination of these two by changing this up a little bit. Yeah, the justification for that is you got to take Calc 5. Sorry. Yeah, I'm not going to go into that right now. But so the solution we had doesn't work. This is a special case. Okay. Let's see if that's true. Let's go back to the calculator and see what the calculator says. Let's enter. Well, it's the same thing except there's a 1 instead of a 2, right? All right. So let's see what the calculator is. Hello. What happened to the calculator? Okay. I just want to copy this and change the 2 ohms, right? The 2 ohms here to 1 ohm. You guys do circuits in physics? No, you never do circuits in physics? You didn't do electricity and magnetism in physics C, did you? You lead a sheltered life. I know you did. And look what it says. It's e to the negative t over 2 like we have, factored out a constant times t plus a constant. A constant times t plus a constant. Yeah, it's the same thing. All right, so our original solution wasn't correct. This is like a correction factor. A special case, don't worry about it. If you wrote it the other way on your homework, that's okay. All right, so now, what about... Well, I mean, we can answer question D now. Go to D.
We're not doing C?
Yeah, we're doing C. Hang on. How did reducing the resistance of the circuit affect the accumulated charge in the capacitor? Compare results from 4A and 4B. And the only difference was we went from the overdamped case to the, that's it, critically damped case. All right, and you can graph it and maybe throw in some initial conditions and whatnot. All right, C. All right, so C says, okay, let L equal 8 henries.
I only have 7 henries.
Sorry, I got 8. And keep the resistance as 2 ohms from the, like at the beginning, and the capacitance at 4 farads like at the beginning. Oh wait, 4 farads is humongous. What?
Let's make it 10 farads.
That's not really a realistic circuit. But anyway, all right. So what happens is you have 8 q double prime plus 2 q prime plus q over 4, right? So it's the same as 4a, except you got an 8 in front instead of a 1 in front. So let's do it. Here we go. 4c. 8 q double prime plus 2 q prime plus q over 4 equals 0. All right. So the last question, part D, also asks what happens when you change the inductance, when you increase the inductance. Okay, compare solution A to solution C. The solution A is still the overdamped, right? All right. So what happens here? Well, the critical. No, I shouldn't say that. I should say the characteristic equation for R is. What would you write? 8R squared plus 2R plus 1/4 equals 0. And you know you could multiply everything by 4 and see if it's a tricky chart or something. But I think the discriminant here is negative. Yeah. So let's go. We're gonna get complex case. Now remember the complex solution? Okay. So R is what? Do the quadratic formula again. -2 plus or minus square root of 4 minus 4 times 8 times 1/4. So the 4 is canceling to get an 8, and 4 minus 8 is -4. So rad -4 is going to give you, but don't forget it's 2 times 8 on the bottom, right? So you got -2 plus or minus 2i over 16, or how about -1/9 plus or minus I over 9? Is it?
It's 1/8 and 16.
Oh, it's 16. What are we doing? You know, it's bound to happen. It's a 16th, right? And reduces to 8ths. All right, so now that you have a complex case, you remember the solution? The solution is supposed to be e to the alpha t times a cosine beta t plus b sine beta t, where alpha is the real part of the R and beta is the imaginary coefficient, not positive or negative, just the absolute value. So how should I write this? E to the negative t over 8 times some constant we can get from initial conditions, cosine of beta is 1/8, just the 1/8, the coefficient of I, and again not positive or negative. So t over 8 plus b sine t over 8. And so the next question in part D, or maybe it's part E, is what happens when you increase the inductance. Compare solution 4A to 4C. 4A was overdamped. This is underdamped. When b squared minus 4ac is negative, we call this underdamped. Under. Not undamped. What am I writing? Underdamped. Which means there's some oscillation, right? Now this kind of oscillation, what does it look like? What's happening to the amplitude? It's decreasing, so it's doing this, and then it's settling down, right? Okay. But what if this 1/8 here, what if this was actually 0? What if this piece right here was 0? So e to the 0 would be 1, and then you get back to that original Hooke's law solution we did in 108?
Yeah.
Okay, we call that's not just underdamped. That's a special case of underdamped. That's undamped. That's like a perpetual motion machine. This is but this no such thing, right? Right, in motion in the vacuum, right? Or yeah.
Okay, let's stay on the homework. You did the A cosine sine stuff.
Is that what?
Is that okay?
You did C,
Yeah.
and this is part C.
Okay.
Yeah, that only applies when you have complex roots in your characteristic equation. Which part did you do that? Oh, silly you!
I did it wrong. I'm sorry.
You did it wrongly.
You
All right.
pretended to say that.
All right, now.
I agree.
All right, now. So go back 1 second. What if there was no resistor? This is a new question. So I don't know homework. What if there's no resistor? What if it's like, let's pick an easy case. How about it's Q double prime plus 4Q? Just a different case. That's the right. But notice that that's a special case of this. What we did when we assumed that the solution was sinusoidal, and there was omega was a square root of the coefficient of the Q or the S, right? We were making assumptions. Now we've proven it because that's a special case of this. Look, try that. What if it's Q double prime plus 4Q? Right? Change it completely. Now what's the characteristic equation? R squared plus 4, because there's no Q prime. So it's 0Q, right? So 0R. So what's R? Exactly. So R squared is negative 4, makes R plus or minus 2I, right? So you're still taking the square root of the 4, right? So what happens if you write it this way? E to the alpha t, A cosine beta t, plus B sine beta t. Who's alpha now? What's the real part of this imaginary number? If your characteristic solution is strictly imaginary, the real part is 0. So this drops out, and you get back to this original case that we did with Hooke's law without resistance. So this is a special case of what we're doing today. There's a bit more powerful solution method. It covers everything. It covers what we did in 108. So this is what we call the undamped case, right? So if not only is the discriminant 0, but the alpha, no, the discriminant is less than 0, but the alpha is 0. It's not underdamped, it's undamped. It's just sinusoidal forever. It doesn't decrease, it doesn't increase. Remember what happens if alpha is positive? It's going like this, and eventually the bridge blows up. You ever see that clip of the Tacoma Narrows Bridge disaster? The bridge goes like this, and then it goes like this, and it goes.
Can we watch it like now?
Can we watch it like now?
That's so calculated.
Okay. Well, wait. Well, let's finish. Wait. Let's finish it. So Q of t is going to be what? Alpha is 0, so that drops out. A cosine beta is 2t plus b sine 2t. So isn't that what we used to do? Without the characteristic equation, when we went straight from here to here, right? All right, now, did we check all our solutions? What was the last one we did? We did B. All right, what was C? C was, we have a 2 here again, and an 8 here, right? All right, let's check that, all right? So, let's go up. That's not, what is going on with you? There you go, it's away. All right, so part C was, we got the 2 ohms again. But now we have 8 henries. And is that what we said? Right? It was a constant in front of the cosine, a constant in front of the sine, the C5, C6. E to the negative 1/8 t, the alpha was negative 1/8. And the beta was at 1/8. Yeah, that's what we said, right? Yeah. And then we perturbed it a little bit and we said, okay, what if it's Q double prime plus 4Q? That's it. Then we don't even get the e to the stuff, we just get the sines and the cosines. Let's see, let's try that again. So I'm going to get rid of this. Let's see, actually want to get rid of this. There you go. And put the 4 in front, right? Then I'm going to get rid of this. This whole term. And I think we put a 1 in front, right? Just for the sake of argument, make it easy. And let's see if that Q double prime plus 4Q equals 0 with respect to t, solve for Q as a function of t. And again, some constant in front of the sine, some constant in front of the cosine, and the 4 is the omega squared, so the 2 is the omega. Remember the omega frequency thing we were doing? Okay? And there you go.
Connor?
Connor.
Special delivery in Aurora.
And Aurora.
Anyone else, just sorry to interrupt, anyone else turn in senior pictures, baby pictures for the senior yearbook?
Okay.
Yes, no?
Yes, no, maybe?
Eight.
She's returning senior baby pictures for the senior yearbook.
And,
Why would I?
I'm sorry, I can't hear you. Okay, I'll look for.
All right. So, that's it. I think we did it. Did we finish? Did we answer every question on here? The bridge? Can we find that? All right, wait. We did D. What's the difference between A and B? What's C, E? What's the difference between 4A overdamped, 4C underdamped, right? And then we have also underdamped and critically damped, and that's for me, and that's it. All right, so that's it. There's your last screencast of the year. Life after calculus, as we know it, is over. Alrighty? Any questions, any comments, any problems, anyone? No? Okay, YouTube, I hope you enjoyed that. Have a nice day.